Board misalignment. Okay. So, good morning, all of you. Am I audible to you? And is the screen visible to all of you? If yes, please say yes. Is that okay to all of you? Am I audible to all of you? Please say yes. If yes. Good morning, Dinesh. Am I audible to all of you? Okay. So, see here. So, now, okay. So, good. So, is everything going fine? So, basically, this is lecture 2 on Introduction to Basic Thermodynamics. So, see here. So, if you recall yesterday's class, we have defined how basic thermodynamics got evaluated from the history, and we have seen some basic terminologies in yesterday's class. Correct? If you remember, we have seen what is a thermodynamic system. Then we have defined what is the surroundings, and after that we have seen boundary, where boundary is the separating entity between system and surroundings. Correct? Now, after defining the system, surroundings, and boundary, we have defined types of systems. Correct? Basically, we have seen closed system, open system, and also one special case of closed system where even energy interactions are not possible are called isolated systems. That's what we have seen. And after that, we have discussed some properties, and we have classified the property of a system into two types, basically extensive properties and intensive properties. Correct? So extensive properties are basically the properties which depends on the extent of the system, and intensive properties are the properties which do not depend on the extent of the system. And we have seen some mathematical analysis how to identify whether a property is an extensive property or an intensive property. Correct? This is what we have seen in yesterday's class, basically. Correct? Is this what we have seen? So can we continue today's class? Is there any doubt in yesterday's class? Is that okay? So this is what we have seen yesterday's class. Correct? So I hope no doubts. So see here. We'll continue. So before continuing, I would like to give one important point which I didn't give actually here. So see here. An isolated system is the one in which both mass and energy interactions cannot take place across the boundary. Correct? This is what we have defined as the isolated system yesterday. Across the boundary. But I would like to add one more small sentence to here. But energy transformation can take place within the system. Okay. And so this line which I have written in bracket is very important, which actually gives us law of conservation of energy. Because in a universe, energy can't come into the universe or out of the universe, because we treated universe as an isolated system. But you see a lot of processes that happen inside this universe, which results in change of one form of energy to another form of energy. Correct? So this line I would like to add, which I didn't actually in yesterday's class. So you could take this, but energy transformation can take place within the system. Means, for example, if you have a tank, let me put this onto the top. Okay. So for example, if you have a tank which is insulated basically, which means no heat can transfer across the boundary. Yeah, it shouldn't cross boundary basically. So if there is some mass inside this, now when there is mass, definitely I told you it will possess some energy, which you call it as internal energy, which you deal probably in tomorrow's class. So see here, insulated having some mass, it's not having any work interaction that's taking place, and also since this is insulated a rigid tank, so even mass can't go in or out of the system. So if you see, if you draw the boundary of the system, then if you see, this mass can't transfer this boundary, and also heat cannot come into the boundary because of this insulation, and also there's, let us assume there's no work interaction. Then suppose if there is fuel, and if this fuel is getting ignited, for example, in such cases, the chemical energy which is present inside the fuel can get converted to heat energy, resulting in a rise in temperature and pressure of the elements inside the tank. But no mass or no energy can transfer out of this green line, which is the boundary here in this case. Okay, so this is what we have seen in yesterday's class basically. And before going to the today's lecture, in yesterday's class we have seen what is pressure and what is temperature as well. Okay? For pressure, we have seen how to write absolute pressure values when gauge pressure is given to you, and also when atmospheric pressure is given to you. Correct? And we have also seen the standard atmospheric pressure as 1 atm is equal to P atm is equal to 1.01325 bar, which is equal to 101.325 kilopascals. Correct? This is what we have seen. It's 101 actually, correct? This one, okay, now it's coming. I hope the board is a little bit less responsive today. 76 centimeters of Hg and all these things, correct? And temperature, I told you, as temperature is defined as the degree of measure to measure. I mean, temperature is a measurable quantity that signifies the degree of hotness or coldness of a body, correct? So based on this principle, you know, there is one principle that got evolved, which is called pressure temperature relation. Pressure temperature relation. Okay, so see here, this board is not responsive today, so I expect there is a bit lag in your systems. Previous class notes, I will make it available. So see here, basically what's the pressure temperature relation that came into existence. So now see here, so yesterday in one class I told you kinetic energy of gas molecules is equal to 3/2 into some constant K into T, where this T is absolute temperature, correct? And I told you pressure exerted by a gas is due to momentum transfer between molecules and walls of the container, correct? This is how you will get pressure, because of the collisions of the molecules with the cylinder walls. So now see here, so what they have done is they have tested different gases and they have plotted this pressure versus temperature curves. Okay, so if you see, basically by the time they gave this, there is no kinetic theory of gases, and which was evolved later, but experimentally they found something. See here, first of all they took one gas and plotted pressure versus temperature. Of course this temperature is in degrees centigrade. Okay, so we can go for negative, so for example -10, -20, all these things. So this is for gas 1, for any gas that they took. Okay, so now they have taken another gas and also they have plotted P versus T. So when they plotted, they got something like this, gas 2. So similarly, they have conducted this experiment for many gases at different combinations. So, but they found one important thing, that when extrapolated, all these curves are meeting at one point. Okay, so they found this. All these curves, when they extrapolated, they are meeting at a particular point, and this point is defined as absolute zero temperature. Absolute zero temperature where this pressure P tends to 0. If you see pressure, if you see this is the coordinate system, then the value of pressure at this point is 0. Correct? So this is what they observed experimentally. Means they have taken different gases at constant volume, of course, and they started plotting this pressure with respect to temperature. And that means basically if you take some constant volume of gas in a container, and by some source if you are increasing the temperature, then pressure is getting increased. So they started to increase temperature and they found pressure to be increasing. But when they extrapolated these lines, they have seen that these two lines are meeting at a point, and they have defined this temperature as absolute zero temperature at which this total molecular motion stops. Means molecules come to dead state, which means there is no velocity of the molecules and just molecules are simply lying within the container without any motion. Because if there is molecular motion, then definitely there should be pressure, correct? Because when molecules are in motion, they'll collide with the container walls and the net effect is some raising the pressure. But if you see with this case, at temperature to be very negative, at some particular value of temperature, the pressure is ceasing, which means the molecular motion stops. So this temperature is absolute zero temperature, and experimentally they found it to be minus 273.15 degrees centigrade. Okay, so this value of temperature is found to be minus 273.15 degrees centigrade. Okay, so this is temperature scale. Correct? Yes, this is the temperature that they found. Later, when they found kinetic theory of gases, K is equal to 3 by 2 into Kt, some constant into T, where T is absolute temperature. So they came to know one thing, that this temperature at which this molecular motion is stopping is this absolute zero temperature. Because if Ke is equal to 0, then this T should also be 0, which means absolute temperature is 0. Which means they thought of bringing one scale in coordination with this degree Celsius, such that this T in degree Celsius is equal to 273.15 degrees K. Okay, let me write the things. If this is in Kelvin, then 273.15 Kelvin plus T degrees centigrade. This is the relation that they obtained. You can adjust the things here a bit, plus T degrees centigrade. So this is the equation they found, and they defined this scale as absolute temperature scale, where T in Kelvin is 273.15 plus T degrees centigrade, because they want to take this minus 273.15 degrees centigrade as the absolute zero in order to introduce this kinetic theory of gases. Okay, so that's why they defined this scale as T of K is equal to 273.15 plus T in degrees centigrade in order to retain this value as absolute zero scale of temperature, absolute zero temperature value. So, and this is why for converting any temperature in degrees centigrade, you will be adding 273.15 to make it get converted to absolute scale, which is Kelvin scale. Okay. Yeah, V is directly proportional to root T. It's not T. Okay. Because kinetic energy, if you see, half m V square, so V is proportional to root T but not T. Okay, so see here. Are you all clear how this relation got established for developing the scale of absolute temperature? This is absolute temperature scale. Okay, clear? There is decimal point here. I hope it's not visible for you in the video. You can highlight this. Okay, can we move ahead for next thing? If you say yes, we can move ahead. Okay, so whenever if you see some straight line like this, you know the equation of this line, if suppose if this is y and if this is x, then the equation of this line is y is equal to mx plus c, which is the equation of a straight line in math basics. Correct? So see here. So if you see, if this is pressure and if this is temperature in degrees centigrade, now one thing, you got a line like this for pressure versus temperature plot, which means you can write pressure is equal to some constant plus B into, or else you can always write, if y is equal to mx plus c, then definitely x can also be written in terms of y, and they gave an expression like T is equal to A plus B into P. Means they gave the relation that this temperature and pressure both are linearly related to each other by conducting experiments. Okay, and this happened when they have dealt this in degrees Celsius. Now suppose if you write this scale in Kelvin scale, then you know your horizon could shifted here because this is the absolute zero in temperatures Kelvin, correct? So if you plot this with respect to Kelvin scale, then if this is the pressure, then you would have got your line like this, because in Kelvin scale this vertical axis which is here means basically this horizon has got shifted by minus 273.15. so this is the line, so which means you'll get a relation T is equal to some constant into P, which means pressure and temperature are linearly related for gases. That's what they came to know at that point of time, and later which was also formulated by Charles law, at constant volumes pressure is directly proportional to temperatures. Okay, but this is the experimental background that is beyond that for getting this pressure temperature relation of gases. Yes, y is equal to x, some constant into x basically. So see here, this is how the relation between temperature and pressure is found to be linear. Okay, clear? So now after defining this, we'll go for the next points. Are you all clear so far? Is that okay to all of you? We are going ahead. Now, if you say yes, I'll move ahead. Okay, so see here. So now we'll go for next definitions in basic thermodynamics. Okay, so we have seen basically what is a thermodynamic system, then we have seen properties, and in properties we define two different properties, like first two different properties, basically pressure and temperature. Okay? So now since you know temperature, what is the temperature and all, I would like to define one thing that's called thermal equilibrium. Thermal equilibrium. Okay, so don't confuse this thermal equilibrium with thermodynamic equilibrium. Okay, there is one more equilibrium in thermodynamics which is called thermodynamic equilibrium, which I'll deal in next lectures, but for the time being please understand what is thermal equilibrium. We can write two bodies A and B are said to be in thermal equilibrium, are said to be in thermal equilibrium if they are at same temperature. If they are at same temperature. Okay, so for the how to convert mm of Hg to bar, I'll tell you when I just give me a moment, but please for the time being take this. So two bodies A and B are said to be in thermal equilibrium if they are at same temperature. Means the equality of temperature is the only condition to say that two bodies are in thermal equilibrium with each other. Okay, so with the help of this thermal equilibrium definition, I would like to write some statement which is also named as zeroth law of thermodynamics. Zeroth law of thermodynamics. Okay, so let us formulate what is this zeroth law of thermodynamics. Okay, yeah, Rohit, I think good morning Ajay. So see here, zeroth law of thermodynamics. If two bodies A and B are in thermal equilibrium with each other, thermal equilibrium with each other, and B is in equilibrium and B is in thermal equilibrium with B is in thermal equilibrium with another body C, then we say, is the skin clearly visible to you? I hope there is no blur. Correct? Is there any blur for you? Means is the writing clearly visible to you, or if something is wrong? Okay, clear, fine. Okay, see here, because for me it's appearing a bit blurred, so I was asking this question. Then we say that both A and C are in thermal equilibrium. Thermal equilibrium. Okay. So actually seeing this zeroth law of thermodynamics was introduced after the invention of first law, because first law is more fundamental than zeroth law. Okay. So but since this law is very very fundamental in nature, this law was named as zeroth law of thermodynamics because it was introduced after the first law. So we don't have number one to give for this. Okay. So this is named as zeroth law. So if you want me to explain this to a diagram, see here. Let us suppose there are three bodies. Okay. Let me use some diagrammatic features that's available here. Okay. So let us see. Let us suppose there is one body A. Okay. So this is basically body A. Okay. Now let us suppose there is one more body B. Okay. So this is body B. And let us suppose there is one more body which is C. Okay, so let us suppose this is body C. Okay, so now if these are three bodies that are available with you, let us suppose this body A is at a temperature TA and this body B is at temperature TB and this body C is at temperature TC. Now what this thermodynamic zeroth law tells us, if TA and TB are in thermal equilibrium with each other, means if TA is equal to TB and if B and C are also in thermal equilibrium with each other, means if TB is equal to TC, then both A and C are in thermal equilibrium with each other, which is TA is equal to TC, which you can see mathematically also here at this instant. Because if TA is same as TB and if TB is equal to TC, then TA is same as TC. Correct? This is what called symmetric relation in mathematics. If X is equal to Y and Y is equal to Z, then X is same as Z. Okay, this is what you see mathematically. Now physically, if you see what's happening, see if there is any temperature difference here in between these two, then definitely some heat gets transferred between body A and body B. Correct? Because heat is a form of energy which transfers from one place to another place by virtue of temperature difference. Means for the heat transfer to occur, the main driving potential is temperature difference. Correct? So if there is some temperature difference, then definitely some heat should flow between these two bodies. But we are assuming that these two bodies are in thermal equilibrium, means no heat interaction is taking place. Net heat interaction is taking place between the bodies. Similarly, if you see body B and body C are in thermal equilibrium, again no heat interaction is taking place between the bodies. Correct? If no heat interaction is taking place between these two, net heat interaction is taking place between these two bodies, then definitely this TB and TC should be same. Correct? Where when TA is same as TB and if TB is same as TC, then definitely this should be 0. So one important point, actually this is a very quite simple property, but one important result they observed from this is for two bodies to be in thermal equilibrium, for two bodies to be in thermal equilibrium, means to have same temperature. Basically for two bodies to be in thermal equilibrium, the bodies need not be in physical contact. Need not be in physical contact. Okay. Yes, if body B and C are in thermal equilibrium, then TA is same as TC. Correct? So see here. Now this is one very important result they came to know, because now if you see heat gets transferred from this body to this body because of conduction through these surfaces, and similarly heat also gets transferred from B to C because of conduction between these two surfaces as well, correct? So which means there is a chance that heat can flow from body A to body C to this body B as intermediate body, correct? Which means even though if A and C are not in physically contact with each other, because if you see here A and C are separated by this particular body B, which means this A and C are not in physical contact. Even though when they are not in physical contact, as long as this body B is allowing heat to transfer, means basically this we call in thermodynamics terms as diathermic. Adiabatic wall is something that prevents heat interaction. Diathermic wall is which is one that supports heat interaction. Okay, means if you give some heat at this end of the body, this body is capable of transferring this heat throughout this body and transfer it to other end. Okay, so basically they have some conductivity. That's what I mean to say here. Okay, so as long as this happens, the bodies are not in physical contact, and of course if they are separated by a diathermic body which allows heat interaction, then these two bodies A and C can attain thermal equilibrium. That's what the main art, and this gave rise to one very important concept called this principle gave rise to the concept of thermometer. Thermometer, yes, thermometer means basically this concept gave the rise for the concept of thermometers. Yeah, I'll explain you what is an adiabatic, isochoic, and all these things. See, adiabatic means basically the process which doesn't allow heat interactions. Okay, so isobaric is at constant pressures and isochoic is at constant volumes. Of course, I'll deal these things in a more detailed way when we discuss chapter 2, basically second module, energy and its interactions. Then we'll see there. Okay, so this thermometer is the main art that studies temperature measurement. Okay, and for this zeroth law of thermodynamics is the one which laid a strong foundation. Because if you see, I hope many of you might have got fever since your childhood and you might have visited hospital, correct? So now if you see the thermometer they are putting on your tongue, now see, your tongue is at the temperature of your body, correct? Now you can't taste mercury actually, because mercury is a very dangerous liquid to go inside the human when it goes inside the human body, correct? So then what happens? There is a glass in between in between your tongue and the mercury, correct? So which means when you touch glass with your tongue, then heat gets transferred from your tongue to the glass of the thermometer. And when glass is in contact with mercury, which is inside this thermometer, heat gets transferred from glass to mercury. Correct? Means the heat which is coming from your body is going to mercury via the glass that is in between, like this. Your tongue is transferring heat to the glass, and this glass is transferring heat to mercury. And finally, the mercury which is lying here is capable of measuring your body temperature within some less time. Okay, so this is what it gave the concept of thermometer in a very keen detail. So because till that moment you don't have basic devices to measure the temperatures of your human body, correct? So see here. So that's why once the concept of thermometer came, then they started designing thermometers. Okay, now how typically a thermometer is designed means if I take a minute to explain you how thermometer works, let me tell you. You might have heard this term gamma, which is coefficient of volumetric expansion. Coefficient of volumetric expansion. Coefficient of volumetric expansion means at a point, if you take a fluid, if you take a liquid basically or a gas, at a given volume, now if you increase the temperature of this particular substance by 1 unit, means by 1 Kelvin, then what's the change in its volume? That's what this gamma tells us, correct? So see here. Yeah, bodies need not be in physical contact. That's what I told you for final body A and C. So see here, this is gamma. Now see, let us suppose this is your thermometer, one typical thermometer that I am drawing here for you. Okay, let me draw the bulb clearly so that you can. So there is one bulb, okay, here, something like this. So now see here, or else let me put a neat sketch for you. Okay, so I hope now it's clear. Now let us suppose you have mercury filled inside this glass tube. There's a top for this with some readings here. Things like this. Correct? Now see, when heat is getting transferred into the mercury through the glass, because this heat, the source of this heat is your human body. Whenever you're putting your thermometer on your tongue, definitely heat gets transferred from your body to thermometric glass tube. And this glass tube allows this heat to flow into the mercury. And because of this coefficient of volumetric expansion that is available for every liquid, there is a change delta V in the volume of mercury inside the tube. Correct? Because when temperature increases, fluids expand generally. So volume of mercury increases. Mercury increases. Okay, so now you know the diameter of this glass tube. So then you decide this delta V is equal to area into delta X. Correct. So you know this delta V, you know this A, because your diameter of this test tube, this thermometer is in your interest. Then you know what is the delta X, means what's the level this thermometer reading or level of mercury is raising, so that you can guess what's the increase in your temperature of your body. So they'll classify whether you are getting fever or not. Okay, so all temperature measurements are based on zeroth law. No, to be frank, this is the case with old thermometers, the thermometers which you see, which you have seen in the past. But now there are a lot of digital electronics that came into picture to measure temperatures. Okay, so for temperature measurement, you have like resistance meters and all these things. But this is the case I'm talking about long days back. Okay. So based on this height increase, you will guess by what amount your temperature of the body got increased. Okay. So now once you define this thermometer, then there are different scales to measure, and there are different scales to measure temperature. So let us see. Temperature scales. So now, for any temperature scale that you design, you should have a lower reading and an upper reading. Correct? Definitely. No, actually types of thermometers is not in the syllabus of GATE, it's syllabus of ESE, which I'm not dealing in this course right now, but you need to, it's enough if you study zeroth law of thermodynamics. Okay, but this temperature scales is in some questions are being asked, so I am giving this data for you. So this is called ice point, which is basically the lowermost limit of the temperature scale, and this is called steam point. Okay, and because this temperature, you can't define temperature exactly, you can just say it's a measure of measuring hotness or coldness of a body. Correct? So definitely when you are designing some thermometer, you should have some standard to fix the lower limit and also to fix the upper limit. Correct? So the lower limit is taken as ice point, where ice and water coexist together at atmospheric pressure. Correct? So normally if you see during atmospheric pressure, 1 atm pressure, ice and water, means basically ice starts melting at 0 degrees centigrade. Correct? So when ice starts melting, there is a combination of water with ice at atmospheric pressure. The value is 0 degrees centigrade. 0 degrees centigrade. Correct? So now in steam point, this is the phase, this point is the temperature where at atmospheric pressure both water and water vapor coexist together, and water starts boiling at 100 degrees centigrade when atmospheric pressure is 1 atm. Correct? So this is taken as 100 degrees centigrade is the reference. Correct? So now this 0 degree centigrade is taken as the ice point, and this 100 degree centigrade as taken as the steam point in this Celsius scale for the international standard of temperature measurement. Now, so if you want to generate any new scale, now that new scale should correspond to the temperature variation between these two limits. Correct? So if you want to draw Kelvin scale, you have just seen 0 degrees centigrade is same as 273.15 Kelvin. Correct? Because we have shown this in today's class in the beginning at this point with this experiment of gas with respect to temperature. Correct? So if you see, this temperature scale could have this lower limit as 273.15 Kelvin, and this upper limit as 100, which means 373.15 Kelvin, because 100 degrees centigrade means 373.15 Kelvin. Difference between steam and vapor, actually both are same, but you call it as steam when the fluid is water, but generally you call it as vapor when it is in gaseous phase of any substance. There is actually some difference between gas and vapor, which I will deal in the coming class, in the next lecture, hopefully. Gas and vapor, these two terms are used synonymously, but there is some difference between these two. I'll talk about this in next lecture. Okay, so see here, 273.15 Kelvin to 373.15 Kelvin, and this is Kelvin scale. Kelvin scale. Now there are two more scales which I could give you actually. One is Fahrenheit scale. Fahrenheit scale, where he divided this 100 divisions length into 180 degrees totally, 32 degrees Fahrenheit to 212 degrees Fahrenheit. And there is one more scale if you would like to see, which is Rankine scale. Rankine scale, where this is 492 Rankine to 672 Rankine. Basically, he also divided this 100 divisions into 180 divisions. Okay, so now what's the law that's governing thermodynamics? So if you keep on like this, you can keep on inventing as number of scales as you need. Correct? So for having some standard measurement, thermometric law is given as, for reading on a scale, it is given by they are defined with respect to if this is ice point, if this is steam point, and for example, if this is a temperature X on your new scale, where this is the temperature on some arbitrary scale, so now if you see, it is given as X minus, okay, let me use capital since I used capital there, X minus ice point divided by steam point minus ice point. Steam point minus ice point is always a constant. Means constant for all scales. Means if you take two different scales, then definitely this value X minus ice point by steam point minus ice point should be constant whenever you consider another two scales. Okay, so for example, if you see, let us suppose this is a Celsius scale, 0 degrees C, and if this is 100 degrees C, and let us suppose you got a value of 40 degrees, okay, let us put this as X. Okay, so now let us take Fahrenheit scale, which is 32 degrees Fahrenheit is the lower ice point and 212 degrees Fahrenheit is the upper steam point. So now if you take 98 degrees Fahrenheit, which is human body temperature, lower fixed and upper fixed points, basically they are called as ice points and steam points. So see here, so basically if you see on a Fahrenheit scale, if the temperature of a body is read as 98 degrees Fahrenheit, then what's the corresponding temperature on the degrees Celsius? Now let us apply this thermodynamic law, okay, for this temperature scale of measurement. Okay, so if you see, let me draw the diagrams again so you can see the things clearly. 0 degrees C, 100 degrees C, and you want to know what's the reading on this scale for a body whose temperature is given as 98 degrees Fahrenheit on Fahrenheit scale. Okay, so means if a Fahrenheit scale reads the temperature of a body as 98 degrees Fahrenheit, then what's the reading of the temperature of the same body on Celsius scale? This is the main thing. Correct? See, if you see, x minus ice point divided by steam point minus ice point should be constant for all the scales that you consider at a time, correct? So if you see, x is the reading here, so x minus, what is the ice point of Celsius scale? 0, correct? Because ice point is 0 degrees Celsius, so 0 divided by steam point minus ice point, which is 100 minus 0. This should be same as the same value when evaluated using Fahrenheit scale. Here the reading is 98 minus ice point, which is 32, divided by steam point minus ice point, correct? So this quantity for all scales should remain same. If I consider one more scale, again that should be equal to something minus, depending upon the reading, minus ice point divided by steam point minus ice point. So if you evaluate this value, this implies x by 100 is equal to 98 minus 32 is something like 66 divided by 180. So if you cancel 1 0, then 6 table goes 11 times and 3 times here. So if you see, x is equal to 110 divided by 3. So if you go for the values, 3 9 times, then 18 times and 86 6. And if you round off this, you will be getting 36.7 for the next reading. Okay, so which means this 98 degrees Fahrenheit on Fahrenheit scale corresponds to a temperature of 36.7 degrees centigrade on Celsius scale. So did you understand now how to calculate the reading on a particular scale where temperature is given by another scale? Okay, so because of this thermodynamic law, for reading on a scale, this value has to be constant for any given scale. Okay, so this 36.7 degrees is actually a body temperature in general, because this 98.4 Fahrenheit is the normal human body temperature when everything is fine within your health. Okay, so this is why zeroth law came into existence for temperature measurement, and then evolved a lot of scales for temperature measurement. Okay, so, and this is how you identify the reading on a particular scale when temperature is given by another scale. Okay. Clear so far? Taken this? Okay, so we learned what is a zeroth law of thermodynamics, and then we have seen the concept of thermometry. Okay. Now we'll go for some basic definitions again that we involve during the course. Can I go for next definitions? So these 4 scales are of basic importance, and to be precise, in today's later modern day, we use this Kelvin scale at utmost importance, because this Kelvin is the absolute SI unit of temperature. So we confine ourselves to the Kelvin scale in general practices. And what are the devices that we are getting nowadays are measuring the temperature with respect to Kelvin in general. Okay. So I'm moving ahead. So now we have seen what is zeroth law of thermodynamics, and we have seen for the bodies to be in physical contact, for the bodies to be in thermal equilibrium with each other, they need not be in physical contact directly, correct? So now if you see, we have seen the concept of temperature, concept of thermometry, and we have seen how to evaluate a reading on different scales. Okay, so relation between centigrade and Rankine. Okay, you want me to do that? Okay, I would like to tell you for your interest. Relation between centigrade and Rankine. And Rankine scale. So see here. Let us suppose your Celsius scale is reading C degrees and your Rankine scale is reading some R. Okay, so see here. This is Celsius scale, which is having 0 degrees centigrade as ice point and 100 degrees centigrade as steam point. So if you see, if you consider Rankine cycle, sorry, not Rankine cycle, we didn't go to that extent still, Rankine scale. So if you see, this is 32 degrees Fahrenheit, and we call that as 32 sorry, not Fahrenheit, 492 Rankine and 672 Rankine. So if this is the case, now see, let us suppose this scale is reading a value equal to C, where this reading is given as C, and let us suppose this reading on the scale is corresponds to R. Okay, so it means if basically if two scales are showing two different numbers, of course they'll show different numbers because these numbers of lower and upper fixed points are not same, correct? So if you apply this law of thermodynamics, thermodynamic law for scale temperature scales, C minus 0 divided by 100 minus 0 is equal to R minus 492 divided by 672 minus 492. So if you see, C by 100 is equal to R minus 492 divided by 180. So if you know R, you can calculate C, or else if C is given, you can calculate R. Now could you tell me what's the relation between Celsius and Fahrenheit scales? Could you tell me what's the relation between centigrade and Fahrenheit scales? C into 1.8 plus 32. F is equal to 1.8 C plus 32. That's what you are telling. 5 into F minus 32 by 19. Okay, C by 100 is equal to F minus 32 by 180. Correct. Okay, so all of you are correct. So if you see relation between Celsius and Fahrenheit scale, Celsius and Fahrenheit scale. So if you see, this Celsius scale has lower limit to be 0 degrees Celsius and upper limit to be 100 degrees Celsius. Basically the ice point and steam point are defined like this for Celsius scale. And for Fahrenheit scale, we just seen this is defined as 32 degrees Fahrenheit and 212 degrees Fahrenheit. Okay, so this is for Fahrenheit scale. So if this show the different readings of C here, and if this shows a reading of F here, okay, then the relation between C and F is given by C minus 0 by 100 minus 0 is equal to F minus 32 divided by 212 minus 32. Okay, so this implies C by 100 is equal to F minus 32 divided by 180. So if you can simplify the things, or else if it's fine even if you leave it like this, because you can always simplify the things. Okay, so if you can cancel two zeros, then 5 9, so C is equal to 5 by 9 into F minus 32, all these things coming to maths calculations parts. Okay, so are you all clear? Now if I give you two different temperature scales, and if I give you the reading on one scale, can you find the reading on other scale for the existing knowledge that you have? Yes, can you all find? See, some 30 people are watching this, so I need your responses. Clear? Ajay, so I hope everyone is okay with this. So if you're okay, we'll go for the next basic terminologies that are involved. Okay, so see here, I'm getting so many yes, I'm happy for this. So see here, we'll go for before going for one point, I would like to give one value for you to understand this. See here. Now, if I want to know a particular temperature where this Celsius scale and Fahrenheit scale both will show the same reading, for a same temperature, these two generally show different readings because this scale is divided into 100 units and this scale has also been divided into 180 units, correct? But for a particular temperature, the reading on these two scales will become same. Can you tell the temperature? What is that? Means the temperature at which both readings on these two scales will be same. Numerically, they show the same value. Can you say that? Where is that? What's the temperature for Celsius and Fahrenheit scales? Any one of you? Vivek, Ajay, Dinesh, Vijay Sai, and all. Absolute. Abhinandan. Okay. 44. No, see actually what happens. 273 Kelvin, which means 72 minus 40. Correct, Pawan, you are correct. So minus 40, because see, if reading on Celsius and Fahrenheit are same, reading on Celsius and Fahrenheit is same, this implies C minus 0 by 100 minus 0 is equal to, see, if this is also showing same reading, we can put C minus 32 by 180, correct, which is 212 minus 32, correct, minus 40, correct. So Vasavi, correct. So sir, correct. So see here. So if this is the case, so see here, C by 100 is equal to C minus 32 divided by 180. So if you cancel 20 table, this cancels 5 times, this is 9 times, which implies 4C is equal to minus 5 into 32. Let me write this clearly. 5 into 32. Okay, so 4 cancels this 32 8 times. So C is equal to minus 40. So minus 40 degrees centigrade is same as minus 40 Fahrenheit. Okay, so on Fahrenheit, both show same reading at minus 40 degrees. Okay, clear? So now I'm going for next terminologies in thermodynamics. Okay, so see here. So basically we have seen different types of systems, and also we have seen what are properties, and we have defined property and temperature. So once we know the definition of what's the temperature is, we have defined something called thermal equilibrium, and from thermal equilibrium we define zeroth law of thermodynamics, which gave the concept of thermometry actually. And we have seen different temperature scales and how to identify readings on a scale when reading on another scale is given for the same temperature, correct. So now I would like to extend my discussion to another basic terminologies that are involved in thermodynamics. Okay, so state of a system. State of a system. State means condition, basically. We'll write the same thing. Condition of the system. Condition of the system. Condition of the system is called its state. So state of the system is specified by its state of the system is specified by the properties of a system. And you know what are properties already, correct? Properties of the system means, for example, let us suppose you have a container like this, where there is some gas inside this, which is at a pressure P and temperature T. Of course, I am dealing absolute temperatures T of K. Okay, so now if you see this pressure P and temperature T tells the condition of this system, basically, correct? Means if I want to ask gas, how are you? Then the gas should tell me, yes, I am at a pressure of P and temperature at some T, correct? So which means this properties of this gas tells what is the situation of this gas, correct? So if you want to plot it on a P versus T axis, P, T, so now depending upon these values of P and T, you will plot the system some as a point on some axis. Okay, it can be PT or PV or any other things, but generally we involve TV, PT diagrams as well, and also T entropy diagrams in the next cases. So this condition or state of a system is defined by its properties. Okay, so if this gas changes its pressure or temperature, any two properties, yeah, generally for gases or for single composition substances, any two intensive properties will define the state of a system. How many properties you need? Basically, I'll deal later in the module of properties of pure substances. There is something called Gibbs phase rule, where we decide how many properties you need to fix the state of a system. Okay, but for the time being, let us trust the system of the condition of the system is defined by its properties. Okay, so two properties are generally sufficient for plotting a gas. plotting state of a gas. So let us plot this as the condition. Okay. Now let us suppose some heat is getting transferred out of this. Then definitely there will be some, change in the system. Let us suppose that is something like this, somewhere here, anywhere as you wish, because I didn't mention what's the process and all. Basically I want to say that the system changes its condition. Okay, so let us go for next definition. Process. Process. Okay, so now a system is said to be underwent a process if it changes its state. If it changes its state. Okay. So a system is said to be underwent a process if it changes its state. Means, for example, if you say, if this is some PT curve, and generally suppose if you say, if this is the initial state and the system changed from this state to this state, means for example something like this, then you say a process has been occurred from 1 to 2. Basically there is a change of state, because if you see here the pressure of the gas is something like this and temperature is something like this, but if you come to the state 2, its pressure got decreased and temperature is increased in general. Okay, so there can be things like this, or generally if you write this as, you can write N2 properties generally as volume, for example. Then these are the how this change in states between 1 to 2 implies that the system underwent a process. Okay, now what is this process and all, we'll see. Okay, but generally we say some process has occurred between 1 and 2 because of the change in its state. Okay, so now I would like to define one very important definition in thermodynamics, which is called quasi-static process. Quasi-static process. Okay, so let us see what is this quasi-static process. Okay, no, quasi-static process need not be reversible. We'll talk why. So please see here. Okay, Dinesh, quasi-static process need not be reversible. Let us see what's a quasi-static process. A process is said to be quasi-static if the process occurs infinitesimally slow, keeping all the intensive properties uniform throughout the system. Okay, now if you see, let us talk about this definition in a closed manner. Okay, so infinitesimally slow, keeping all the intensive properties uniform throughout the system. Why all the intensive properties are to be uniform? Let us see here. Now let us consider a piston cylinder arrangement. Okay, or else let me draw with the help of lines for you. This board is I think a bit less responsive today. Okay, so see here, let us suppose we have a cylinder like this. Yeah, something like this. Okay. Next, let us suppose you have another line like this, and there is a piston like this to you. Okay. Now in this piston, there is in a cylinder. Let us suppose there is a piston for you. This is taking time, I think. So we'll draw manually whatever is available to us. I think it's not responding. So please see here. We'll draw manually because it's taking time. So see, let us suppose there is a piston like this. Okay. So now let us try to plot pressure versus volume. Okay. Specific volume oils, because you have some mass inside this. So when you know what's the volume, you know what is specific volume. Okay? Because volume divided by mass is nothing but specific. I have given you specific properties. Okay? What's the meaning of uniform throughout the system? That's what I'm going to tell you now. So see here. Let us suppose initially some gas is packed in this system. Okay, all of you, please don't write anything. I'll give you time. See here. Let us suppose there is gas at every point in this system. Okay. Correct. So initially we assume all the properties are same are uniform throughout. Means, for example, if the value of pressure at this point is P1, then definitely value of this pressure at this point is also P1. Means at every point, if you consider the properties, they are same. Means if pressure, temperature, specific volume at this point is same as at this point and also same as at this point, at every point, if the values are same, then we say the properties are uniformly distributed throughout the system. Normally, if we keep the system by its own to itself, it will attain equilibrium, which means at every point there will be some uniform concentration of the volumes and all these things. Correct. So now let us suppose there are some jumps on this. Your jumps packet you will be getting. This is a small cylinder. So let us suppose there are some jumps on this. Okay. So at this moment, if you see, if P is the pressure, so see here, if I draw this piston free body diagram, so see here what happens. Now, if you write the forces on this, there is weight because of this jumps. Yes or no? Now, bottom there is pressure of the gas because the gas is at some temperature, so molecules don't sit silently. They'll start exerting a pressure P on the surface of the bottom surface of the piston. Correct? So these are the forces that are acting. Suppose if you neglect weight of the piston, which are generally lightweight pistons. So if piston weight is neglected, if P is the pressure of the gas which is lying here, then this is how the free body diagram of the piston looks like. Correct? Yeah, G, I'm telling you, that's why weight of the piston is neglected. Okay. Generally pistons are made of aluminum and all, lightweight pistons. So please let us try to neglect the weight of the piston. So if you see, P into area of the piston will give you weight. Correct? Because at equilibrium, if piston is not moving, then definitely this equation should get satisfied. Yes or no? Because the downward force should be equal to upward force. Because if there is no net motion of the piston in this vertical direction, then definitely this piston must be in equilibrium. Correct? If it is in equilibrium, sigma Fy is equal to 0 from your statistics. From your statics, sigma Fy is equal to 0. So if sigma Fy is equal to 0, the bottom force is P into area of the piston is same as weight of jumps on the piston. Correct? So if you see, that's the case. So pressure is uniformly transmitted throughout this gas, and this whole gas is assumed to be at some pressure and at some volume. So definitely you will get the state of the gas somewhere here. Okay, this is initial state or first state. Now, let us suppose you are sitting here on a table comfortably and you are eating these jumps. Okay, so by the time you eat this first jump, let us suppose you finished this first jump, that is lying here. Then what happens? This weight on the piston decreases, correct? Because whatever the jumps that are here is exerting some weight on this piston. So by the time you hit first jump, number of jumps that are lying on the top of this piston decreases, which means some weight on the piston decreases, correct? So some weight on the piston decreases, then what happens? This pressure decreases. How this pressure is decreased? Generally, there is nothing, no position for the mass to escape. Then when you are taking this block, then what should happen for the pressure to decrease? Volume should increase, because you know pressure and volume are inversely proportional to each other. So if pressure want to decrease, your volume should slightly increase, which means this piston which is initially here will move a bit high. Correct? Means it get displaced in this vertical direction by a very small amount. So now if you see with this equation, when W of jumps is decreasing, because you have finished one jump, so this pressure is decreasing. So pressure decreases, and if you see when pressure decreases, to attain this decrease in pressure, this piston moves up, which means volume slightly increases. Correct? Now volume increases, but there is no change in the mass. Then what happens to specific volume? All of you? If volume increases and if mass remains constant because of the closed system here, then what happens to specific volume of the gas? All of you, please tell me what happens to the specific volume of the gas? It increases or decreases? Expand means it increases or decreases? Increases, correct? Vivek, all of you, increases. So when it increases, the system which is initially at state 1, when your all jumps are sitting here, has got somewhere here. Okay, let me use white color. Yeah. So your pressure slightly decreased and your volume slightly increased, which you can see in the diagram. So this is state 2 when you finished one jump. So similarly, let us suppose you consumed one more jump, which is here. So then what happens? Still the pressure decreases by some amount, and this W is slightly decreasing. So again, your process occurs like this. So if you keep on eating all these jumps, then what happens? This piston starts coming up slowly, and at every state, you know what is the states that's happening. 5, 6. Correct? Now see here, why I am supposing to put this pressure as single point. Look, because when I take one jump, when the piston moves up slowly, between the time gap that you are taking another jump, this pressure gets settled throughout this chamber. Correct? P increases and W P also decreases. Correct? If you see, pressure is decreasing throughout this path because P is directly proportional to this weight of the jumps, so this decreases. And volume is increasing. Dinesh, am I clear why P is not increasing? P is decreasing because of the movement of the piston. Okay, so see here carefully. So now, okay, so if you see, this process is occurring infinitesimally small, and I am sure enough, since this process is occurring infinitesimally small, I have sufficient time for the properties to transfer uniformly throughout the system or the chamber, correct? Because if you see, let us suppose if I replace all this weight with a single weight like this. Let us suppose there is a piston like this, and let us suppose there is a weight, single block of weight W, which is equal to the weight of the jumps. Now, if I remove this block, what happens? This piston all of a sudden lifts up. Correct? Yeah, atmospheric pressure affects the piston, but I'm not considering it, assuming this pressure of gas to be very high. So please see here, this W. Correct? Now, if I take this W at once, means instead of removing part by part, if I take this weight all of a sudden, then what happens to this piston? This piston, which is initially here, raises up suddenly. Correct? By the time it raises up suddenly, let me draw a bigger diagram so you can see the things. If this is initial position of the piston, and if this is final position, okay, let us suppose this is initial and this is final position of the system. Now see here carefully. In this case, when your weight is in small portions, your piston is moving from this equilibrium position to this equilibrium position very slowly, correct? Which means you are able to identify the states. If suppose if this 1 is the initial state and if this 6 is the final state here, then you know this every intermediate path, every intermediate state of the system between the initial and final states. But now if you replace this weight with one single weight W, and if you take that weight, then what happens? The piston which is initially here gets displaced here. When this piston immediately moves here, see what happens carefully. We'll talk about these molecules of gas which are here. See, if piston moves all of a sudden, whenever this piston has moved all of a sudden, there will be some enough space for these molecules on the first line to move immediately up. Correct? Which means pressure at this instant will fall quite low. But if you talk about molecules which are at the bottom, they need some time to start moving, because ahead of all these molecules there is some restriction. Correct? So which means for the transfer of pressure to be uniform throughout, they need some time to redistribute the pressure, to distribute the properties. Correct? To a uniformity all over the chamber. So which means if this moves all of a sudden, then the pressure here is very low and the pressure here is same as the previous pressure. Then which value you will put here? Correct? So for plotting the states, your process has to be quasi-statically low. I mean the process has to occur very slowly, which means quasi-statically. Understood? So for quasi-static process, you know all the intermediate states. But for a non-quasi-static process which happens very rapid, you just know, you can write this is quasi-static and PV, if this is 1 and if this is 6, you can write this process. You can write it with a dotted line because you don't know basically what are the intermediate states. Correct? So non-quasi-static. Correct? Because in non-quasi-static process, you don't know what are the intermediate states, because the pressure of gas shifts suddenly from here to here. But in case of quasi-static process, when you are removing, you know each and every intermediate state. So that's why you could generally join this quasi-static process when all points are known to you. But in non-quasi-static process, you know you're not aware of the intermediate points. So generally you denote non-quasi-statics with a dotted line. Okay. Clear so far? Now I will give you some time to take the notes, so please take it. Did you all understand why there should be uniformity in the intensive properties? Because if I want to plot a pressure P here, then definitely that P should be same throughout the cylinder at every point. And that happens only if you give enough time for the molecules to settle, and that happens only in case of quasi-static process. Clear to all of you? Now please take these things. I'll give you some time. You can take this, and once you finish you can say yes, then we'll continue ahead. Is it understandable to all of you? Is there any doubts to any of you? Yes, at every point it's in equilibrium, because this equation you are writing considering equilibrium of this piston. So please take this. Reversible and irreversible is the next step. I'll go to that point now, once if you understand what is quasi-static process. In mod, plus and minus are equal. Okay, where did I put modulus meanwhile? I hope no. Correct. Is audio okay? Means am I audible to you? Am I audible to you? Okay. Yes. Then just a second. Here I think there is some issue with my mic. Just a second. Okay, so see here. So now we understood what is a quasi-static process basically. Okay, now we'll see what's the definition of reversible and irreversible processes. Okay, so let us do that. Okay, so reversible process, which is very important because generally we do all our analysis considering the processes to be reversible. Okay, now see here, reversible process. A process, or you can say to be more precise, a thermodynamic process is said to be reversible, is said to be, I'll tell you why can't we retrieve back non-quasi-static process. See here, a thermodynamic process is said to be reversible if the process can be reversed, to the same initial state, Now one thing I would like to write here with a different ink, which is very important, along the same intermediate equilibrium states, along the same intermediate equilibrium states, leaving no effect on the surroundings, Yes, correct Vivek, leaving no effect on the external things on the system. Okay, no effect on the surroundings. So this process is really important. Yeah, along the same path, which means basically along the same intermediate equilibrium states. Now see here, let us assume a quasi-static process. Okay, so now let us take a piston cylinder again, which is something like this, and let us suppose there is a piston here. Okay, so let us suppose this is a piston. Which is tightly fitted into this cylinder. Okay, so see here. Now let us suppose there is some gas here inside this. Okay, so now let us do something, an excess part. Let us restrict this piston such that this piston can't move up. Okay, now let us put something here in this part. Let us suppose there is a paddle wheel. Okay, so this paddle wheel is basically carrying some weight W. Okay, so let us suppose this is the initial. Okay, let me draw things clearly with a different ink so you can see. So now let us suppose you have a paddle wheel which is connected to a weight W. Okay, so now one thing I want to tell you, when this weight falls down, definitely this paddle wheel rotates. Yes or no? Please tell me, because this shaft is mounted with a rope. So whenever this weight is falling, this paddle wheel starts rotating. Correct? Yes. Correct? Yes or no? Will this paddle wheel get rotated when this weight is coming down? Are you all okay at that till that point? Yes or no? All of you, nearly some 30 people on live. Reply yes or no. Okay. So see here, only 3-4 people are responding quite, frequently. What about others? So please see here. So when these wheels are rotating, look, I want to tell you in a very close way. See here, when this paddle wheel is rotating with the gas, tell me one thing: will the paddle wheel and the molecules of gas rub each other against each other? Means basically when this paddle wheel is rotating, this paddle wheel and gas molecules will rub each other. Because of friction, some heat gets liberated. Yes or no? Clear? Yes. So which means temperature and pressure of this will get increased slightly. Correct? So see here, if you understand all these points, so now see clearly. Now, let us suppose this is the first initial point of pressure and temperature inside this. Now, whenever this wheel is rotating slowly, of course, infinitesimally slowly it's rotating. So let us suppose this is passing through all these equilibrium states. Okay, so this is a closed system and definitely no mass can go out or in, but energy interactions, work interaction is taking place since this is a closed system. Okay, so see here, let us suppose this is the final state by the time this weight which is here got displaced to this point W. Okay, clear? So now if you see, because of this falling of weight from this point to this point, this wheel got rotated, and as a result of some friction between the molecules and this, this paddle wheel, some temperature, there is some rise in the temperature slowly. And of course, you see, I have seen at constant volumes, since temperature and pressure are directly proportional to each other, which we have seen, this pressure also increases. And of course, meanwhile, when this weight is here somewhere in between and at the third point, then definitely we can plot all this intermediate states. Yes, or 2, 3, 4, 5, 6 basically. Correct? Now this process is quasi-static, definitely, because let us suppose we are reducing the weight so slowly so that this paddle wheel gets rotated very much slowly, and definitely this temperature and pressure increases. So now see here what happens. If the process is before one of you are asking me, if a process is quasi-static, can it be reversible? No, actually, because if you say this process is quasi-static, correct? If you say this process is quasi-static, now definitely if this temperature and pressure, which is because of this heat getting generated here, now if you transfer back that heat Q back to the atmosphere again, look, there is temperature T because of the friction between the molecules and this paddle wheel. Now definitely the small amount of heat that got liberated, let us suppose that is coming out, because mass can't come out but energy can come out, so which means heat is coming out. Then what happens? Again, this system is capable of retracing these paths in a reversible way. Yes or no? Means initially, because of the rotation of the paddle wheel, if the temperature and pressure are slowly increasing step by step, then definitely by the time this heat getting liberated outside, these values come slow again with about the same path. Will you all agree with me? Yes or no? But now if you see, I mentioned one important word here, leaving no effect on the surroundings. Means if you see clearly, this weight which is initially here got displaced here when the piston pressure and temperature are rising. But when heat is coming out and this gas molecules are again tracing back the same path, this weight won't go up again. Correct? Means if you take this gas as the system which is inside here, if you take this gas as the system, and this blue line as the boundary, So everything external to this gas will be observed as a surroundings, and if you see, there is an effect of the effect on the surroundings, which means the weight which came down won't go up again, even though the gas comes back to the initial state because of some heat loss. Correct? Yes or no? Clear? Yes or no? All of you, please respond. Do you all understand? Even though because of some heat transfer, even if the system is coming back to the same state, but this weight which is in the bottom can't go up. Correct? So if that's the case, which means even though the system is retracing its path back to the same equilibrium states, but it's leaving an effect on the externals of the system, surroundings of the system. So which means this process, if you see within the system, there is no irreversibility, which means the system is always approaching the same path. But if you see, there is an effect on the surroundings, which means this process is not totally irreversible. Process is not totally irreversible. Process is not totally irreversible. Correct. So which means if you see within internal to the system, then the process assumes to be irreversible. But if it's leaving some effect on the surroundings, then you can't say the process is totally irreversible. So for this purpose, we define two important terms called internally irreversible and externally also irreversible. Okay. If you consider this particular process at this instant, this is only internally irreversible but not externally, because this weight which is sitting here has fallen down and this weight won't come up. Okay, so there is some effect on the surroundings, which means this process is only internally irreversible, okay, but not externally. Yes, frictionless quasi-static process we consider it as reversible, and we call that as isentropic process, which we introduce the name later in later stages. So did you all understand why even if process is happening quasi-statically, why it can't be reversible? Are you all okay at that point, till that point? So if a process is quasi-static, it need not be reversible. Okay, clear to all of you? Clear to all of you? Yes or no? I need more responses. Around some 30 people are watching this. What about others? So please respond. Yes? Yes, in the past example, it's reversible. But see, a reversible process is always quasi-static, but a quasi-static process need not be always reversible. Okay, so we'll write that statement here. A quasi-static process need not be reversible. Okay, so this is the main outcome of today's class that I want you to observe. Okay, so a quasi-static process can't be reversible. Okay, so it's 11:29. We'll resume our discussion here for tomorrow's class. For quasi-static, internal reversible is compulsory to be. Ajay, I don't understand your question, so please you can ask in a bit modified way. So please see here. We'll stop this lecture here because it's already 11:30. So we'll end up the class now. So if you have any doubts, you can talk to me, or else if everything is going fine, then we can continue in the tomorrow's class. Okay. Yeah, definitely I'll explain what are different types of works, but of course that's not our point of interest here. Just I'm defining what is a reversible process and all. In second module, I'll definitely give you the expressions for steering work, basically the paddle wheel work, electrical work, different forms of work. We'll see what are there in present. Okay, Pawan, so no issues. In second chapter, I'll deal all those kinds of works, so no problem. So is the thing okay? Do you all agree with me with this point till now? If it's okay, then we'll wind up today's session. Is everything clear to all of you? Is the explanation understandable to all of you? All of you, please respond. Around some 30 people are there. Yes? Okay? Crystal clear? Okay, then fine. So we'll meet tomorrow at 10 o'clock sharp. So please be attentive. Don't miss any lecture. Okay? Because if you see, this is a continuous subject. Every lecture has some connection with the previous lectures. So don't skip any lecture that happens. Okay? So fine. Take care, all of you. We'll meet tomorrow.